Okay, let's do a typical example problem for chapter 12. I'm just going to make one up, and it's very similar to other ones like number 9 and other problems in chapter 12. So let's say that at time 0, like 2 months ago or something, I'm trying to make this very time relevant. So at time 0, there were 100 people in Washington State with the coronavirus. So that would be P0, the population at time 0 was 100. And again, I don't know, I'm just making up these numbers, it's probably something like that. So let's say we start off with 100 people with the coronavirus. And then let's say that they start noticing that it doubled every 6 days. So every 6 days, there are twice as many. Which, I don't know, sometimes you hear 2 or 3 days or something. So every 6 days, there are double. So the doubling time is 6 days. Okay? So what is the model? What is the exponential model for this population? So then what we do is we'd say, okay, the population is P0 e to the RT. And we know what P0 is, that's the starting one. That's already 100, or if it's easy to find out, we plug in T equals 0 here. Anything to the 0 is 1, so the population at time 0 is 100. So we know right away that the population is 100 times e to the growth rate, that's what R is, times how many days have gone by. We'll say how many days have gone by. Well, we don't know the growth rate, we just know it doubles every 6 days. But that's all we need. So in 6 days, we have 200, right? So right now there's 100. In 6 days, we have 200. In 12 days, we have 400. In 18 days, we have 800. You get the idea. In 24 days, we have double that, 1600. It doubles every 6 days. So all we need is one of these data points. Might as well take the first one. In 6 days, it's 200. So the population with coronavirus in 6 days, P at 6, is 200, and that's equal to 100 e to the R times 6, because our time is 6. Okay, well that's easy. Put the 100 over here, divide both sides by 100. We have 2 is equal to e to the 6R. It's always nice to put the number first, so I did that there. We want to solve for R, but it's up here in the exponent. But fortunately, we learned about logarithms, and since our base is e, we want to use a natural log. So take the ln of both sides. So we have the ln of 2 is equal to the ln of e to the 6r. And fortunately, we know that ln and e are inverse functions. They cancel each other out. That's why we took the ln. ln of an exponent cancel each other out. All we're left with is what's up here. So ln of 2 is equal to 6r, or r then is equal to, let's see, the ln of 2 divided by 6. ln of 2 is a number that comes up a whole lot. It's worth memorizing. It's 0.6931, and that 1, you know, it's small. If you don't include it, it's not that big a deal. But I might as well have it here. So that's divided by 6. And if we do that, we get about, let me try that, 0.6931 divided by 6. That's 0.1155, which means, since this is an E, we can immediately say that is the daily growth rate, since we're talking about days. So you'd say it's growing at 0.1155, or 11.55%. That's the nice thing about dealing with E, because then R is directly the growth rate. That is how fast it grows per day, at 11.55% per day. Since we're dealing with days, if it was per year, we'd say that was years. Okay, now we know how the population grows. It's P is equal to 100 e to the 0.1155 t. And t is in days, and that would be the answer to our problem. That would be a model of how fast that grows. I put that in my calculator, And it looks something like this, the standard exponential curve that you hear about in the paper so much. It gets bigger and bigger and bigger, faster and faster and faster. And nothing gets bigger faster than exponents. Putting the t in the exponent is way bigger growth than even like t to the 100. This might start graph growing faster, but exponents always, exponential growth where the t is in the exponent always catches up and will always win in the long run. Okay, that's a typical example problem. You're given 2 points. All you need are 2 points to figure this out. We know the first point, and we know the point at 6 days, 12 days, whatever. And then we can figure out what the growth rate is. We have to use logarithms, the skills that we learned for practicing, and we can figure out a formula then for the population. Now we can figure out what the population will be anytime we want. So let's figure that out just for the fun of it. Let's say 100 days later, when t is 100, how many people will have it? So it's 100 e to the 0.1155 times 100 in 100 days. I went to 24 days out here. It was 1600. So again, this is doubling every 6 days. So I'll put that in my calculator. See, that'd be 11.55 times 100. So I get that, ooh, that's bad. That would be, 100 times that's 11.55. So let me try that again. It seems like so many people. 11.55 times 100. It's 1037703.68. Let's put some commas there. That's 10 million people.
Oh God.
After only 100 days, if it keeps growing that way, which is why everybody's so scared of exponential growth. It goes crazy. Now, there aren't even 10 million people in Washington, so obviously it can't continue to grow that fast. But that's, again, how fast exponential growth is. It doesn't seem that bad at 12 days or 24 days, but at 100 days, it's like more than everybody in the state has it. Okay, so that's a typical example. Let me do a few other examples to help you out with some of the math. Like for the first one, I think I already did some examples in another video, but let's look at like E for number 12.3. So 12.3 E. And that says that y is equal to 3 times 14.24 to the 4t. And we want to write that in standard exponential form, which is y is equal to a0, the amount, that's why they use a, the amount at 0, e, oh wait, actually they mean the amount at 0, e to the at. Okay, we want to write that as something as e to the at, and the advantage of that is that a then is the growth rate. It tells you immediately, oh, 11.5% or whatever, you know immediately how fast it grows. But it doesn't look like that at all. So we got to figure this out. So first, let's see. We want this thing in here to be an e. So we can say y is equal to 3 times 14.24 to the 4th to the t power. And now we can do 14.24 to the 4th, because remember, powers multiply, so power to the power is 4t there. But let's do the 14.24 to the t first. So 14.24 to the 4th power is a very, very big number. So that's equal to 3 times 4, 118.75506 to the t power. And I'm going to keep all the decimals just because I can. It's not that much work. Okay, so, but that is not an e to the a power. So the way we can do that one is use the properties of logarithms that we've been learning. And it turns out that if we have some base b to the power t, that's the same thing as e to the ln of the base to the power t. And that's really easy to show how that works. I can work that out. I think they work that out in the book, how that works, but that's basically all you got to know is you have a base to the t, that's e, the natural log of the base to the t. So all you got to do is take the natural log of 4.118 of that. So the natural log of all that nonsense, 4.118.75506. Now I got to plug that in my calculator. 0.75506 natural log. I get 1.4138. Let's say 1.414. 1.414. So that would be y equals 3 times e to the 1.414 t. So this relation here is really important. It helps you out a lot. That if you have a base to the t, that's the same as e to the natural log of the base to the t. So get familiar with that natural log base number in your calculator. Okay, so that would be it. This is why A0 is 3. The growth rate is 141%. That's a really big growth rate in this case, this example, times t. Okay, that's one example. Let me do one more example from one of the math problems later on. They say solve the following equations for x. So this is 12.8. I'll do the last one here, which is f. They say solve for x. 2 to the 3x plus 5 equals 3 squared equals 3 squared. We want to know what x is. Okay, first off, that's 9. It's not too crazy. So let's just write that. So 2 to the 3x plus 5 is equal to 9. Now, we don't want to get this 2 here is messing things up. 2 to some power, like well, we want to get that x out. So to get rid of a 2, we take log base 2 of both sides. But we don't have a log base 2 on your calculator. So instead, you just take the ln of both sides. And you could take regular log too. There's no reason it has to be natural log, but it just seems like natural log is the thing to use. So take the natural log of both sides. Natural log is something to a power is the power times the natural log. So that's where that comes in. Make sure to use parentheses here. It's the power, which is 3x plus 5, times the natural log of 2. Again, natural log of a number to power is the power times the natural log of that number. That's equal to the ln of 9. Divide both sides by the ln of 2. So then we get 3x plus 5 is equal to the ln of 9 divided by the ln of 2. That's just a number you can plug into your calculator. And if you're really clever, we know that the rule we learned before, that ln, actually, no, that's not the case. Sorry. You can't be too clever here. If it was ln of 9 over 2, we could use that relationship. It's ln of 9 divided by ln of 2. You just got to plug that in your calculator. What's ln of 9 divided by ln of 2? Okay, subtract 5 from both sides. 3x is equal to ln of 9 over ln of 2 minus 5. Let's just get that number out now. So 9 ln divided by 2 equals that, minus 5 equals that. I get negative 1.83. Divide that by 3. So x is negative 1.83 divided by 3. So I get that that's negative 0.61. Okay, so that's how you solve those. You got to use those rules we learned, which come in really handy. By getting rid of things, taking the natural log of both sides to get rid of exponents. And then just getting good with the buttons in your calculator and doing algebra. Okay, hope that helps.